Hello, chemistry honors students! You thought you could escape me for one day. However, I made a screencast for you just to ensure that your chemical education will continue as we talk about atomic structure and the different parts of the atom. So, recalling what we learned from our simulation, when we mess with protons, you mess with the entire element. Today we're going to talk about what happens when you mess with the neutrons and when you mess with the electrons. Remember, the neutrons are found in the nucleus of an atom, just like with the protons, and the electrons are found outside of the atom in what we call electron clouds. All right, so you are on your side of the notes that says isotopes. So first, let's figure out what an isotope is. So isotopes are atoms of the same element. So they're all of the same elements, which means they have the same number of protons, therefore the same atomic number. Because remember, A stands for atomic number, P stands for protons, E stands for electrons. In a neutral atom, all of those are the same. And the protons designate or dictate what the atomic number is. So all of these isotopes that are listed down below are the same element. Okay, so they're all different atoms of magnesium. The only thing that differs with isotopes is that they have a different number of neutrons. Therefore, they have a different mass number because those neutrons have a mass of 1 AMU. Protons have a mass of 1 AMU. So if you change the number of neutrons, you're changing the mass of the overall atom. So let's just take a look at these different isotopes of magnesium. So all of them have the same atomic number. So in the nuclear notation, you have 12. The 12 designates how many protons are in the atom, which is our atomic number. Then up in the upper left-hand corner of the nuclear notation, we have the mass number. Okay, so now remember, mass number is different than atomic mass. So the mass number for this isotope of magnesium is 24. Remember, man from 8-man, M is your mass number minus your atomic number is going to equal your number of neutrons. So in this case, 24 minus 12 would give us 12 neutrons. So this atom in its nucleus will have 12 protons and it will have 12 neutrons. Okay, over here, this isotope of magnesium. Here we have a mass number of 26 and the atomic number still of 12. So 26 minus 12 equals 14. So this isotope of magnesium has 14 neutrons. Moving over here, this isotope, 30 minus 12 equals 18. This isotope has 18 neutrons. And that's what differs with isotopes. It's the different number of neutrons, therefore giving the atom a different mass number. And we write that in nuclear notation with the mass number in the upper left-hand corner and the atomic number in the lower left-hand corner. All right, so here is an example of two isotopes of sodium. All right, remember that the atomic number is same, so the number of protons are the same. So in this case, we've got 11 protons right here in this atom of sodium. And in this one, we've got 11 protons, right? The thing that's going to differ is going to be how many neutrons are there. So in this particular picture, we have 12 neutrons. In this one, we've got 13 neutrons, okay? Giving it an overall different nuclear notation. So for this isotope of sodium, this would be sodium 24, but again, the atomic number goes in the lower left-hand corner, so both of them are going to have 11 in the lower left-hand corner. Noting that 24 minus 11 is 13, that's going to give us our number of neutrons there. 23 minus 11 equals 12, so we've got the 12 neutrons depicted there. So remember that mass number equals the number of protons plus the number of neutrons. That's for mass number. Very different from atomic mass. Atomic mass is that average atomic mass that we see on the periodic table that always comes with a decimal. So let's just think of those two sodium isotopes that we were just looking at. They both have the atomic number of 11. When we calculate and compare their mass numbers, because one has 12 neutrons and the other has 13 neutrons, they have a different mass number. The very first example has 23 AMU because you have 11 protons and 12 neutrons. Each proton and neutron has a mass of 1 AMU. So in total, it has 23 AMU. And this one over here, because we have one more neutron, is going to have it's going to have a mass number of 24 AMU. Yuck, 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 yuck. My cat might make an appearance here too. All right, so let's check for understanding. Let's go back to that lithium atom that we did before. So lithium has the atomic number of 3, meaning it has 3 protons, okay? What are the mass numbers of its 2 isotopes? Okay, so this first isotope has 3 neutrons. So if you have 3 neutrons, they go right here. How many protons does it have? It has 3. So we've got 3 neutrons. We have to pick a color. So we have 3 neutrons. Oh, this is when it gets really interesting when I start trying to write. 3 neutrons plus 3 protons equals 6 AMU. All right, this isotope has 4 neutrons. So we have 4 neutrons here. We have still 3 protons because its atomic number is 3, meaning it has 3 protons. 4 plus 3 equals 7 AMU. Okay, this is how we calculate the mass numbers for different isotopes. So what do we use isotopes for? Well, isotopes can be used for bone scans or many diagnostic medical devices in order to detect different traveling of fluids through the body. You can detect bone cancer using technetium-99, which is an isotope of technetium. We use different isotopes of barium to detect for leaks in the bowel or in the digestive tract, because what happens is when you have so many neutrons, it can become unstable and radioactive, and then we're able to visualize it using different detective devices. So how do we write out the name of an isotope? This is different than the nuclear connotation that we've been talking about. Writing out the name is pretty simple, but for some reason it seems to be pretty hard for students to remember. All you do is write out the name of the element, put a dash or a hyphen, and then you add the mass number, right? And the mass number is the number of protons plus the number of neutrons. It's really that simple. So for example, those sodium isotopes that we were talking about, we would put sodium dash and 23. That's the mass number. It's really that easy. For the lithium that we were just talking about, you could have lithium dash 6 or lithium dash 7. But that's how you write the name of the isotope. All right, so then how do we write the symbols for an isotope? And that's what I've been talking about most of this time. This is what's called the nuclear symbol. All right, how we write out the nuclear symbol is we show the mass number and the atomic number in the symbol form. And the way that we do that is we put the mass number in the upper left-hand corner from the elemental symbol. So in this case, we're using that sodium example again. So here we have sodium down here, right? And in the upper left-hand, that's where we're going to put our mass number, okay, depending on which isotope we're dealing with. And in the bottom left, we're going to put our atomic number. Now, depending on which isotopes we're talking about, if they're all sodium isotopes, they're all going to have an 11 in their lower left-hand corner because they all have 11 protons, because that's what dictates what the element is. So when we write this and we call it the nuclear symbol. All right, so which of the following represents isotopes of the same element X? Take a few seconds, talk to your shoulder partners, figure out which of these following, A, B, C, or D, represents isotopes of the same element X. Then I want you to figure out what X is. That means you're going to have to pull out your periodic tables and figure out what X is. All right, so these A, C, and D all represent isotopes of the same element. And we know that because they all have the same atomic number, right? When you change the atomic number, it means you're changing the protons, which means you're completely changing the element, okay? These three all have consistent atomic numbers, which means they're all the same element. All right, so we established the first part of the question. A, C, and D all represent isotopes of the same element X. Now we need to identify X. So I know that this says 92. I go to my periodic table and I figure out that 92, or the element that has 92 protons, is uranium. So these are all isotopes of uranium. All right, so now take a few minutes and complete the summary table that's in your notes. I'll have Miss Phillips pause it while you complete the table. So now let's flip over those notes and let's talk about ions and isotopes, or what happens when you change the number of electrons or neutrons. And we were just talking about what happens when you change the number of neutrons, and that was isotopes. All right, so changing parts of an atom. Protons, these are what define an element. You cannot change the protons. You do not mess with the protons. However, you can change the number of electrons. And when we do, it's called an ion. Remember, when we change the number of electrons, it ends up giving that atom a charge. Remember when we talked about charges? Those charges are called ions. They're just charge atoms. When you change the number of neutrons, that's called an isotope, okay? So the number of neutron, if that changes, you've got an isotope. If you've got a change in the number of electrons, you've got a charged atom, and you have an ion. All right, let's take a look at ions. Anything about John Cena is always going to be funny. All right, ions happen when you lose or gain electrons. How sure was the nucleus that he had lost an electron? He was positive. All right, so what is an ion? Ions occur when atoms lose or gain electrons. So what happens when they lose or gain electrons is they're going to acquire an electrical charge. And the reason they acquire an electrical charge is because either the positive protons are winning or the negative electrons are winning, depending on how those electrons are changed. But because they are changed, it's no longer going to be a neutral atom. A neutral atom, remember, is when your protons equal your number of electrons. When we've created an ion, protons and electrons are no longer equal. All right, so it's no longer an atom, but now it's considered an ion. That's the new name given. All right, so here we have that lithium atom that's missing an electron. Remember this? Shots fired. All right, so when you take out this electron, now we only have 2 negative charged electrons left, but we have 3 positive protons. That means the protons are going to win this game, and right now they're winning by 1. So overall, that atom is going to have a +1 charge. It's no longer a neutral atom. It's got a +1 charge to it. All right, so over here, this atom is neutral. This atom has 6 protons, 6 neutrons, and 6 electrons. Okay, this is a neutral atom because the protons equal the amount of electrons. Over here, this atom is going to be negatively charged. And it's going to be negatively charged when electrons outweigh the protons. Not really outweigh, but like there are more electrons than there are protons. So in this case, we have 6 electrons. We have 5 protons, which means this would be an ion, a negative ion, with a charge of -1. Over here, we've got an atom that has 6 protons and 5 electrons, which means those protons are winning that war, and this atom would have a charge overall of +1. So then we have a positive ion. Sorry, my computer's giving me fits here. Come on. All right. Okay, so back to that diagram of the lithium atom. Whoops. Just writing all over everything. All right, so this diagram of the lithium atom. Here we have 3 protons, 2 electrons. We have 1 more proton than we do electrons. Therefore, we have a positive ion of lithium. And the way that we would write that is Li, and then we would put the positive charge on the right-hand side here. I don't have to put the 1 in because if the positive charge is there, it's understood that it has at least 1. If it's more than 1, then you would need to put the number. Okay? So the way that we use ions is, for an example, lithium batteries. So lithium batteries run off of lithium ions, and it's all the transfer of electrons through those lithium ions that keep the battery energized. That's what supplies the voltage for the battery, is the transfer of these lithium ions through an electrolyte. And in that case, the electrolyte solution is it's sulfuric acid, which is HS. So how do we write the symbol for an ion? All right, so the ion symbol is going to be the element symbol, which is easy, right? It's your magnesium, Mg, carbon, C. And then you're going to put the charge in the upper right-hand corner. So whoever's winning that war, if it's protons, make sure you note that it's a positive charge. And then how many are the protons winning by? If it's 2, then you would put +2. So in the last example, we had 1 more proton than we did electron, so we would write Li and then plus in the right-hand corner. If the element symbol has a charge, plus or minus, it is an ion of that element. Lost an electron, you really have to keep an eye on them. All right, so now let's check for understanding. On the left, answer the following. Which of the following are ions? So right now with your table group, I want you guys to discuss which of the following are ions. I'll give you a few minutes. And then talk about how you know they're ions. Here are your answers. So we've got bromine, we've got sodium, we've got fluorine, we've got magnesium, aluminum, and iron. How do we know that they're iron, or how do we know that they're ions? Is because there's a charge expressed in their symbol. So here we have the symbols, the chemical symbols, and in the upper right-hand corner, the ones that we chose as ions have a plus or minus and a number, or it's implied next to them, but they are showing a charge, which means that they are ions. All right, so now, after you've had a little training on ions and isotopes, now what you need to do is that second day of the PhET simulation that we did, now you're going to pull that out. That's a little ways back in your notes after the first day of the PhET. It looks like this. You need to complete this simulation, it's going to, so you're going to need to finish this front page, and then you're going to need to finish the back side of that, okay, along with this worksheet part. So you need to finish that front side of this sheet, the back side of this sheet, and then you need to get an in-class stamp from Miss Phillips. Okay, once you get that in-class stamp, then you can pick up the homework. The way the homework gets glued in is you have a left side to your right side of your notes. Okay, so these are your notes that we just took. This is your left side. This is your ion and isotope doodle page. Your doodle page must have descriptions in these boxes. That includes this box. Just because there's nothing written in it doesn't mean you get to leave it blank. So descriptions in the boxes. Okay, you need to tell me what elements these are based off of their pictures. And then you need to tell me the difference between ions and isotopes. Okay, flipping to the next page. The next page is going to be your homework. Now this is a double-sided homework, and this is going to become a left side of your choice. So that's how this is all going to get glued into the notebook. All right, let me know if you have any questions. Ask Miss Phillips, and maybe she can get a hold of me. But otherwise, good luck. Hope you guys have a good day learning about ions and isotopes. And hopefully that was helpful. Peace.